All right, today we're going to pull back the curtain on one of the coolest tools in all of AI, something that helps machines deal with the messy, uncertain real world. We're talking about Bayesian networks.
You know, have you ever really thought about this? Your spam filter has to guess if an email is junk. A medical app has to guess at a diagnosis from your symptoms. In all these cases, the machine doesn't have all the facts. So, how does it make such a good, educated guess? How does it handle all that uncertainty? So here's the game plan. We're going to tackle this in 5 simple parts. First, we'll talk about why we even need to reason with uncertainty. Then, we'll define what a Bayesian network actually is. After that, we'll build one with a super simple example, lay down some rules with probability, and finally, we'll use it to calculate a real outcome. Trust me, by the end of this, it's all going to click. Okay, so what's the big problem we're really trying to solve here? Well, the world isn't a neat and tidy place with simple yes or no answers, right? It's filled with maybes and what-ifs and probablys. For any AI to be genuinely smart, it has to be able to navigate all that gray area. And the tool for that, the very foundation, is probability.
So what we need is a specific kind of tool, one that's designed to draw a map of all that uncertainty, a way to represent these messy relationships and then reason about them logically. And that tool is the Bayesian network. It's our key to turning a world of probabilities into some pretty solid predictions.
Okay, so we know we need this special framework to handle uncertainty. We know it's called a Bayesian network. But what is it exactly? Like, what does it look like? How is it put together? Now, that definition sounds super academic, I know, but let's just break it down. Think of it like a map. The cities on the map are your variables, things that can happen, like rain or no rain. And the roads connecting the cities? Those show the conditional dependencies, which is just a fancy way of saying how one thing affects another. It's basically a cause and effect map that runs on the rules of probability. And this map has a specific blueprint, a special name, a Directed Acyclic Graph, or you'll often hear it called a DAG. Let's slice that up. Directed is easy. It just means we use one-way arrows to show who influences whom. A causes B. Simple. And acyclic is really important. It means there are no loops. You can't have A causing B, which causes C, which then circles back and causes A again. That would be a logical nightmare. This structure makes sure our cause and effect always flows forward. All right, enough with the theory. The best way to understand this is to actually build one. So let's get our hands dirty with a classic, super intuitive example that's going to make all of this crystal clear. We're going to model a tiny little universe that has just 3 things in it. First, is it raining? Second, is the sprinkler on? And third, is the grass wet? That's it. Super simple, but as you'll see, these 3 things are connected in some pretty interesting ways. So let's draw our map. Let's think logically. What makes the grass wet? Well, either the rain or the sprinkler, right? So we'll draw arrows from rain and from sprinkler, both pointing to wet grass. But wait, there's one more link. You're probably not going to turn your sprinkler on if it's already raining. So rain influences the sprinkler. We'll draw an arrow from rain to sprinkler. And just like that, we've got our map. We've made our DAG. Okay, so we have our visual map of what affects what. But a map isn't much good without distances or details. So now it's time to add the numbers, the probabilities. These numbers are the rules that govern our little universe.
Let's start at the top with our one independent variable, rain. In our model, rain just happens. Nothing else causes it. So we'll just say that on any given day, there's a 20% or 0.2 chance of rain. And of course, that means there's an 80% or 0.8 chance of not rain. Simple as that.
Okay, next up is the sprinkler. Now remember, the sprinkler depends on the rain, so its probabilities are conditional. This little table shows us that if it is raining, the chance of the sprinkler being on is tiny, just 1%. Makes sense. But if it's not raining, the chance of the sprinkler being on goes way up to 40%. See how that works?
And now for the final piece of the puzzle, the wet grass. This one depends on 2 things, both the sprinkler and the rain. So our table needs to cover all 4 possible combinations. For example, if the sprinkler is on and it's raining, well, the grass is almost guaranteed to be wet, a 99% probability. But look down at the bottom. If the sprinkler is off and there's no rain, there's a 0% chance the grass is wet, at least according to our model.
Okay, this is it. We have our map of how things are connected, and we have the probability rules for every single connection. We have officially built a functioning Bayesian network. Now, we can ask it a question and get a precise mathematical answer.
let's ask it something very specific. What is the probability, the exact odds, of this very specific scenario? A world where it is raining, the sprinkler is also on, and the grass is wet. What are the chances of all three of those things being true at the exact same time?
So, to get our answer, we use something called the chain rule. Now, don't let the formula scare you. All it's really saying is that to find the probability of this whole chain of events, we just multiply the individual probabilities together, following the arrows on our map. We start with the probability of the grass being wet, given the other two things are true, then multiply that by the probability of the sprinkler being on, given that it's raining, and finally multiply that by the simple probability of it raining in the first place.
And now we just plug and chug. We just have to look up the numbers we already defined in our tables. So, step 1, probability of wet grass given sprinkler and rain, that's 0.99. Step 2, probability of sprinkler given rain, that's 0.01. And step 3, the base probability of rain, that's 0.2. Now for the easy part, we just multiply those three numbers together.
And there it is, 0.00198. That's less than a 0.2% chance. So what we found is that there's a very, very small but very precisely calculated probability of this exact scenario happening. We didn't just guess. We used logic and math to figure it out.
So let's just zoom out for a second and appreciate what we just did. We took a messy, uncertain situation. We drew a simple map of how all the pieces influence each other. We assigned some common sense probability rules, and then we used that system to calculate the exact likelihood of a pretty complex event. That, right there, is the magic of Bayesian networks.
And this is where your imagination can just run wild. Our little example had just 3 variables. But now imagine a network with thousands or even millions of them. What could you model then? You could model the economy, you could predict weather systems, you could diagnose complex diseases, you could help a self-driving car navigate a chaotic intersection. The possibilities are, and I mean this literally, endless. So the real question is, what would you build?